Welcome back to AI CodeCast. Every single day, we like to dive into a new coding challenge, and today we're tackling a problem.
Yeah.
Classic, the sliding puzzle.
Yeah. You've probably seen these before. I mean, picture a small grid with numbered tiles, right? And one empty space.
Okay.
And the goal is to slide the tiles around to get them in order.
Yeah, like those 15 puzzles, right?
Exactly.
But here's the catch. We're not just trying to solve it, right?
Yeah.
We want to find like the absolute shortest path to the solution.
Most efficient way, yes.
And to make it even spicier, some puzzles you just can't solve.
That's what makes it so interesting. It's not just about moving tiles. It's really understanding the underlying structure and using algorithms to kind of navigate that space.
Okay, I'm ready. Let's dive in. The source material here, it starts us off with a couple of examples. The first one here, it's pretty basic. A 2x3 board with the numbers 1, 2, 3 on the top row. And then 4, a blank space, which is represented by 0, and then 5 on the bottom row. Looks like you could solve this in a single move.
Yeah, deceptively simple. It looks like it, right?
Yeah.
But that's, I guess, kind of the beauty of these puzzles. Even a small change can totally change the solvability and complexity of the entire thing.
Okay, so the very next example, it's almost identical. 1, 2, 3 on top. But then 5, 4, and the 0 on the bottom row. And this one, you can't solve it.
Yeah.
How can such a small change, like, make it unsolvable?
This is where things get a little bit deeper, I guess.
Yeah.
So the solvability of these puzzles is actually determined by something called the parity of the arrangement. Think of it like this. Every time you swap two tiles, you're changing the order of the numbers. Right? So some arrangements require an even number of swaps to get to the solution, while others require an odd number. If your starting arrangement just doesn't match the parity of that solved state, you're never going to get there.
Wow. Okay, so it's not just about, like, randomly sliding tiles around. There's actual math going on behind the scenes. How do we even know if a puzzle is solvable before we start trying to solve it?
Well, there are ways to calculate that parity, before you even start. But I think for today's challenge, let's just assume we're given solvable puzzles. Let's just focus on finding that shortest path.
Okay.
But remember, even with solvable puzzles, the number of possible moves just explodes as the puzzle gets bigger.
Okay, challenge accepted. I'm ready to dive into some algorithms. Where do we begin? Like, how do we systematically approach this thing?
Okay. So one classic approach is called depth-first search, or DFS.
Right.
So imagine you're trying to find your way out of a maze, right?
Okay.
You pick a path, and you just keep going until you hit a dead end or you find the exit. If you hit a dead end, you backtrack and try a different path.
Ah, okay. That's basically what DFS does.
So we're basically just trying all the possible sequences of moves, right? We're sliding that 0 around until we hit the solution. That seems straightforward enough, but I can already see, like, a potential problem. Wouldn't that take, like, forever for larger puzzles?
Yeah, you're right. That's the main drawback of DFS. It's easy to understand, easy to implement, but it becomes incredibly inefficient as the puzzle size grows. The number of possible paths grows very quickly. Kind of like a branching tree. It just gets out of control.
Okay, so DFS might work for small puzzles, like our 2x3 example, but for anything larger, I mean, we'll be sliding tiles till the end of time, basically.
Yeah.
We need something smarter, something that can find that shortest solution without having to explore every single dead end.
You're getting it. So this is where a slightly more sophisticated approach comes in. Breadth-first search, BFS.
BFS, okay. I'm sensing a pattern here. What's so special about this one?
So instead of going like deep down one path at a time, BFS explores the puzzle's possibilities layer by layer. Imagine searching outward from the starting position kind of in waves, like ripples spreading across a pond,
Okay.
You check all the states that are reachable in one move, then all the states you can reach in 2 moves, and so on. And you systematically explore all the possibilities at each distance from the start.
So instead of diving down these rabbit holes, we're carefully, like, expanding our search outward.
Yes.
That sounds promising, but I still feel like we might get lost, like, in the sheer number of possible arrangements.
That's a valid concern, but BFS has a major advantage over DFS. It guarantees finding the shortest path. Since we're exploring in layers, the first time we hit that solution, we know that's the most efficient way to get there.
Okay, so I get it, but I'm curious, is there any way to make BFS even better? Like some secret, like, pro-level technique to speed things up even more?
You're thinking like a true algorithm enthusiast. Yeah, there's a way to kind of supercharged BFS. It's called bidirectional BFS.
Bidirectional. Does that mean we're running BFS like in two directions at the same time?
You got it. So instead of just searching outwards from that starting state, we also launch a BFS search from the end state, the solved configuration.
Whoa. So we're basically having these two searches like race towards each other, hoping that they collide in the middle.
Yeah, I like that analogy. And when those two search frontiers meet, we know we found a path. And because we're using BFS from both ends, it's guaranteed to be the shortest one. And this drastically reduces the search space, especially for larger puzzles.
Okay. I'm starting to see how powerful this can be. It's like having two teams digging a tunnel from opposite ends of a mountain, and the moment they break through, we know we found the most efficient path.
Exactly. Now, let's bring this back down to earth a little bit. We've been talking about these powerful algorithms, but remember, for small puzzles like the 2x3 ones we're focusing on, there's an even simpler approach that can be surprisingly effective.
You mean like a cheat code for small boards?
Kind of, yeah. Think about it. There are only a limited number of possible arrangements for a 2x3 puzzle. What if we calculated all the solutions beforehand and just stored them in a lookup table?
So we're essentially pre-computing all the answers for a specific board size.
It's surprisingly simple, but very effective for these smaller boards. You know, we invest some time up front to calculate all the solutions, and then we get like lightning fast lookups for any given starting configuration.
So it's like we're trading computational effort for instant answers. That's pretty clever.
Yeah, it highlights an important point, that there isn't always one best algorithm. The most effective approach really depends on the constraints of the problem you're trying to solve.
Okay, so I think we've covered a lot of ground here. We went from like the simple kind of brute force approach of DFS. Then we talked about the elegance of BFS, and we even touched on the supercharged bidirectional BFS. And then on top of all that, we learned about like pre-computation for smaller puzzles. It feels like we've unlocked this whole arsenal of techniques for tackling these sliding puzzles.
And that's the point, right? It's not just about memorizing these algorithms. It's about understanding these core concepts and then figuring out how to apply them.
Absolutely. Now, if I'm thinking like a programmer, right? And I need to actually write the code to implement these algorithms, where do I even begin?
Well, I think the first step is figuring out how to represent the board digitally in a way that our code can easily understand and manipulate.
Okay, so we talked about sliding tiles around, but how do we actually represent those moves in code?
Okay, so one way to think about it is swapping the 0, remember that represents our empty space, with one of its neighboring tiles. So we can pre-calculate the valid moves for each position of that 0 and store them. That way, we don't have to recalculate them every time we want to explore a move.
Yeah, that's smart. But I'm still a bit fuzzy on how we'd actually implement these search algorithms, especially like BFS and bidirectional BFS in code.
Okay, so let's visualize this. Imagine you have the initial state of your puzzle, right? You generate all possible states that you can reach in one move. You're essentially creating a new layer of possibilities. And these states are put in a queue. A queue is just a data structure that works on a first in, first out principle. So we take the first state from the queue, explore its possible moves, and add those new states to the back of the queue.
So we're systematically exploring each layer of possibilities, making sure that we don't miss any potential paths. But how do we avoid like getting stuck in these loops where we're like revisiting the same state over and over again?
That's a great question. We have to keep track of the states we've already visited. We can use a set. A set only stores unique elements, so it lets us very efficiently check if we've seen a state before.
Gotcha. So with BFS, we're basically fanning out, checking each layer of possibilities until we hit the solution. What about bidirectional BFS? How do we handle searching from both ends?
So it's kind of like running two BFS searches simultaneously, one from the start state and one from the end state. We use two queues and two sets to track visited states for each search. And the magic happens when we check if a state visited by one search has also been visited by the other.
So the moment we find a state that exists in both of our visited sets, those two searches have collided, and we found the path. And because we're using BFS from both ends, it's got to be the shortest one. That's amazing.
It really is, and it highlights how cool algorithm design can be. Often the most elegant solutions come from a deep understanding of the problem and just being willing to think outside the box.
This is what I love about these codecasts. You always learn something new. Now, I know some folks might be feeling overwhelmed, with all this talk about algorithms and data structures. Is there any advice you would give to someone who's just starting out and wants to tackle this challenge?
Yeah, I think don't be afraid to start simple. You don't have to jump right into implementing the most complex algorithm. Try solving a small puzzle manually, you know. Observe observe your thought process and then try to translate those steps into code.
Yeah.
Even if you start with a brute force approach like DFS, it's a great way to get your feet wet.
Great advice. Start small, understand the basics, and then gradually build up. And remember, there's tons of resources available online, code examples, tutorials, they can help you along the way.
Yeah, absolutely. The key is to break the problem down into these smaller steps that you can manage, right? And just experiment, learn from your mistakes. That's how you truly master something.
Speaking of mastering concepts, this sliding puzzle problem is a popular one in technical interviews. Why do you think interviewers are so fond of it?
Well, I think it's a great way to assess a candidate's problem-solving skills and their understanding of these fundamental algorithms. It's not just about writing the code. It's about analyzing the problem, choosing the right approach, and then being able to clearly explain your thought process.
So it's not just about like memorizing the code. It's about showing that you can think critically and solve problems efficiently.
Yeah,
I can see why that would be valuable.
precisely. The sliding puzzle, it's a deceptively simple problem, but it lets you explore so many different algorithms and data structures. It's almost like a microcosm of the types of challenges that programmers face every day.
Well, I think we've given our listeners a lot to think about. We explored the problem, discussed various approaches, and even, talked about its importance in technical interviews. What final words of wisdom would you offer our aspiring coders before they embark on this challenge?
I think embrace the challenge. Don't be intimidated by the algorithms or the code. Just break the problem down, experiment, and most importantly, have fun.
Okay, so we've talked about all these different approaches to solving the sliding puzzle, but I'm curious, how do we actually turn these like ideas into
All
code?
right, time to kind of roll up our sleeves and get practical. Remember, like, the first hurdle is figuring out how to represent that 2 by 3 board in a way that our code can easily work with.
We talked about sliding tiles around, but how do we actually capture that movement in code? What's
Hmm.
the best way to represent this puzzle digitally?
Well, there's, a few ways, but one straightforward approach is using a simple string.
A string. Really? How does that represent a whole board? Well, think about it. Our 2 by 3 board has 6 positions, right? So a 6-character string could perfectly represent each tile, including that empty space.
Ah, okay. So our example puzzle, the one with the 4, 1, 2 on top and the 5, 0, 3 on the bottom row, that would be like the string 4, 1, 2, 5, 0, 3.
Exactly. And the great thing about using a string is it makes it really easy to compare boards, check if we've seen this board before, and even make those, tile swapping moves.
Okay, I see the elegance there. But how about those moves themselves? Coding the actual act of sliding these tiles around seems like it could get messy.
Yeah, it might seem that way at first, but let's break it down. Remember that rule. We can only swap the 0, the empty space, with an adjacent tile.
So for any given position of the 0 in our string, we need to figure out which indices represent its neighbors.
Exactly. And the cool thing is, for a 2 by 3 board, we can pre-calculate all that. The
Mhm.
0 can only be in 6 possible positions, right? So for each one, we know exactly which indices it can swap with.
So we could create a lookup table, like a dictionary or something, that stores all that information beforehand so that when we're exploring moves, we don't have to recalculate those swaps every time.
Exactly. It's all about optimization.
Efficiency win. Okay, so we've got our board representation. We've got this clever way to handle those swaps.
Mm.
Now, the big question, how do we implement these algorithms?
Okay, this is where the magic happens. So let's start with DFS, right? The one where we go deep down one path at a time. It's all about recursion, calling the same function repeatedly to explore every possible move.
So we'd start with our initial board state, look at the valid moves. And then for each of those moves, we make the swap, create that new board state, and then call the function again.
Right. And with each recursive call, we got to keep track of some things, the path we've taken so far, the number of moves we've made, and whether we've encountered that same board state before helps us avoid getting stuck in those infinite loops.
Gotcha. Okay. Now, what about BFS? That one was where we explore layer by layer.
Right.
How do we manage that in code?
For BFS, we need a queue. That's a data structure that works on this first in, first out principle. We start by adding that initial board state to the queue, along with the number of moves made, which at the start is 0.
And then we enter a loop that keeps running as long as our queue isn't empty. And in each iteration, we take a board state out of the queue, generate its possible next states using our pre-calculated moves,
And this is the key part. We check if any of those next states is the solution. And if we find it, we know we found the shortest path because BFS explores layer by layer. If not, we add those new states to the back of the queue to make sure we're systematically checking everything.
Okay, BFS, it's making sense to me now, but bidirectional BFS, that sounds way more complex to code. How do we manage those two searches happening at the same time?
Actually, it's not as bad as it sounds. It's like running two BFS searches in parallel, one starting from the initial state, the other from the solved state. We use two queues and two sets to keep track of the visited states. And here's the trick. With every new state we generate, we check if it's been visited by the search coming from the other direction.
So if a state shows up in both of those sets of visited states, we know those two searches have collided and we found a path. And since we're using BFS, we know it's the shortest one. That's so clever.
It really is. It shows the power of being creative with algorithms. Sometimes the most efficient solution comes from looking at the problem from multiple perspectives.
I'm so glad we did this deep dive on the sliding puzzle. It's amazing how this simple problem can lead us to all these fascinating algorithms and data structures.
And I hope our listeners feel inspired to try this challenge out. Remember, it's all about breaking down the problem, picking the right tools, and most importantly, having fun.
Exactly. Coding is all about exploring, learning, creating. So go out there, experiment with these algorithms, and have fun solving those sliding puzzles.